In this video, I'm going to explain what multiprocessing is in under 3 minutes. Hello everyone, and welcome back to another video of a series I like to call Tech Explained in Under 3, where we attempt to explain tech concepts in, well, you've guessed it again, once more, in under 3 minutes. In the last video, we talked about what multithreading is and how single cores of processor utilize that execution model to execute threads concurrently. And in this video, we will continue our conversations on operating system execution models by discussing multiprocessing. This video builds up on top of what we talked about in the last video, and so make sure to check out the previous video if you haven't yet before continuing with this video. And if you haven't hit that subscribe button yet, it's time to smash that button now. Oh wait, go ahead. Alright, now that we've got that out of the way, it's time to dive right in. Let's go over a quick recap from the last video. Multithreading is an operating system execution model that allows any computer process to have multiple code segments, called threads, such that these code segments or threads can execute both independently and concurrently, but they share the same process resources. We also made sure to really make the distinction that concurrency is not the same thing as parallelism, in the sense that concurrency's execution method involves progressing multiple tasks in a way that context switched rapidly from one operation to the next, giving us the illusion of parallelism. This model is super ideal in running threads that involve idle time. Like for example, when you send a network request and you need to wait on it until you get a response back from the server. These kinds of operations are known as input-output intensive operations. However, on the other hand, parallelism involves actually progressing multiple tasks simultaneously. So why do we even need parallelism when multithreading's concurrent nature is actually quite efficient and gives us the illusion of parallelism? Once again, excellent question, my friends. Excellent question. Even though multithreading is a rather efficient execution model, at least in comparison when we don't actually have multithreading, there is a limit after which this model ceases to be efficient. The multithreading model works really well when the thread execution contains idle time. And that is because when a thread that is being executed goes idle, like when it waits on something for example, the operating system is free to context switch to the execution of another thread until the idle time of that initial thread comes to an end. And so when we don't actually have idle time in our thread execution, switching from one thread to the next doesn't really serve us any purpose. Running different code segments in multiple threads in this case takes almost the same amount of time as running these code segments in a single thread. It might even take marginally longer because now on top of what we already have with the time of the execution for these code segments, we also have to add the time required for thread context switching into our equation. These kinds of operations where multithreading fails are referred to as computation intensive operations. And examples of these include sorting, searching, graph traversal, and matrices multiplication. And this is exactly why we need multiprocessing. So multiprocessing is an operating system execution model that utilizes the cores of a processor to execute two or more code segments, in this case they're called processes, in an actual parallel fashion. And so if you recall from our multithreading video, if we have a 4-core processor, then we can have 4 processes running at the same time. And if we have 8-core processors, then we can have 8 processes running at the same time. And by that same logic, if we've got a 16-core processor, then we can run 16 simultaneous processes at the same time, and so on. You get the picture. Alright, so let's build on top of a restaurant analogy from the last video then, shall we? Because y'all know how much I love analogies. So let's consider the same restaurant A from the last video, but instead of restaurant A being run by only that one non-efficient cook or a single core who can only prepare one order at a time before attending to the next order or the next thread, we will hire 3 other cooks that prepare orders in the exact same fashion. Recall from the last video that each order preparation involves 2 phases, a 5-minute active preparation phase and a 10-minute cooking idle phase, which doesn't require the cook's involvement whatsoever. So now, restaurant A has 4 cooks or 4-core processors employed, where each cook or core begins their workday by starting the process of cooking, and so totaling 4 processes of cooking per day. But each of them can only work on one order or one thread at a time, which means that if 4 orders or 4 threads come in at the same exact time, they will be distributed among the cooks or the cores in this case, and will be prepared or executed right away without any wait time. And so, as you'd imagine, that's super fast. Thereby, if you go into restaurant A and 4 people are queuing before you, you will only have to wait a total of 15 minutes before a cook or core in this case is freed up and attends to your order or thread, which is better than the 20 minutes wait time from the multi-threaded restaurant B in the last video. This is exactly what happens when you have a multiple cores processor that supports multiprocessing but does not not support multi-threading. Now, let's consider the same restaurant B from the last video, but instead of restaurant B being run by only that one efficient cook or a single core that knows better than to wait idly until the order is ready before starting on with the next one or the next thread, we will hire 3 other cooks that operate in the exact same fashion. So now restaurant B, like restaurant A, has 4 cooks or 4 cores employed, where each cook begins their workday by starting the process of cooking, and so that gives us a total of 4 processes of cooking. In this case, and in contrast to restaurant A, each of these cooks can work on multiple orders or threads at the same time, in the sense that once an order or a thread completes its active preparation phase and goes into its cooking phase, the cook is freed to move on to preparing or executing the next order or thread. So if you go into restaurant B with the same 4 people queuing before you, you only have to wait 5 minutes before a cook attends to your order or thread. Now this is what I'm talking about. This is exactly what happens when a processor supports both multi-threading and multiprocessing execution models. And this hybrid model is how processors operate nowadays. This is absolutely impressive. And time. Here we go again. Overtime again. I don't even know why I try anymore. Nah, I'm just kidding. You know that I love nothing more than rambling to you people. I hope this was helpful in helping you understand what multiprocessing is. Feel free to leave any questions you might have in the comments and I'll answer them, and also let me know which concepts you'd like me to make videos about and I will make videos about them. Thanks for watching and I'll see you in the next video. Peace.